Hi class, today I'm going to work through this Matrices practice quiz that will prepare you for the assessment task. This practice quiz has 12 questions, and for each question there is a little bit of theory that is explained about how the idea works or the skill, how to execute the skill. There's then a practice question that I will do, and then I encourage you to pause the video to complete B before I do it to check that you have understood what is required. So let's get started and work through the quiz. Okay, so number 1, describing the size of a matrix. So every matrix we talk about in terms of how many rows and columns it has. So some matrix n by m matrix has n rows and m columns. That is, there'll be some sort of amount n rows, and then crosswise will be some sort of m columns. So n is sort of the rows and m columns across. So for example, this is a 2 by 3 matrix because it's got 2 rows, 3 columns. So looking at part A, what size is this matrix? Well, it's got 1, 2, 3, 4 rows and 1, 2 columns, so it would be a 4 by 2 matrix. Pause the video and try B for yourself. In B, what size is this? Well, it's got 4 rows, 3 columns, so it will be a 4 by 3 matrix. Question 2. We can use a matrix to represent a system of equations. So here is an example of a system of equations. It's got 3 variables, x, y, and z. And we can write this into a matrix where the coefficients, so the numbers in front of them, of the pronumerals, are written in the matrix. So 2, 5, and 1, you can see that's the first column there. 3, minus 1, and 3, the second one, and then the third one is 1, 3, and there's actually no term for z, which means it's a 0. And then the answers that are on the right hand side there, placing over there. Okay, so we're going to write this matrix, system of equations in matrix form. Okay, so let's do that. It's going to be a 3 by 3 with that extra line, which is going to show that last bit. So on the top row, I've got 1, 1, and 2. On the second row, I've got 2 in front of the x, nothing in front of the y, and 1 in front of the z, and minus 2, 4, and 3, with 10, 8, and 5 going in there. Okay, so just to note that these are all the coefficients of x in the first, then they're the coefficients of the y terms, and they're the coefficients of the z terms. Okay, try B. For B, you would get a matrix like this. On to question 3. So how do we add matrices together? So if you have two matrices, how do you add them together? Well, in order to do that, the matrices must be the same size. E.g., they've got to have the same number of rows and the same number of columns. So you could add a 2 by 3 matrix to another 2 by 3 matrix, but you couldn't add a 2 by 3 to a 4 by 3. And the way we do the adding is we add the two numbers that are in a matching position. So if I'm adding these two matrices together, what matrix am I going to get? I'm going to get another 2 by 2. Now, the first position, which will be here, is going to be a combination of those same positions there. So it'll be 1 plus 2, so it'll be 3. And this next box along will be a combination of 3 and 0, which will be 3. On the bottom, I'll keep following that sort of pattern. Minus 2 plus 4 will give me 2. And then the next one will be 3. 4 plus minus 1. So that gives me my matrix by adding them together. Okay, why don't you try B? Here's the solution for B. Two by 2 matrix, 4, 4, 3, and 2. Question 4, subtracting matrices. When we're subtracting them, the same rules apply as for adding. They've got to be exactly the same size. And you subtract the two numbers that are in matching positions. So on this matrix here, I'm going to go 3 minus 1 for the first. For the second one, I'll do 1 minus 0, which is 1. For the next one, I'll do minus 4 minus 2. So minus 4 minus 2, that's going to actually end up with minus 2 altogether. And we also get minus 2 for the bottom right hand corner. So that is subtracting two matrices. Try the next one. Here's the solution for B. Question 5, multiplying a matrix by a scale factor. So you can multiply any matrix by a number. So you could double it, times it by 5, times it by a half, times it by -2. And when you multiply a matrix, you multiply the number on the outside by all of the values on the inside. So a little bit like if you were, expanding a bracket. You're putting in a factor into each of the parts. Okay, so the first one I'm going to do, for my first term, I'm going to get 3 times 1 for the first part. So I'm doing that one, then I'll do 3 times 0, which will give me 0. And then 3 times minus 2 would give me minus 6. And 3 times 2 will give me positive 6. Try multiplying in B yourself. Here is the solution to B. Multiplying 2 by each of the terms, I get 2, minus 6, 8, and 0. Question 6, multiplying matrices. To be able to multiply two matrices together, the number of columns of the first matrix must equal the number of rows of the second matrix. Okay, so the columns of the first must match the rows of the second. And the matrix that we're going to get, the resulting matrix, is going to have the rows of the first column and the columns of the second matrix. Okay, there's lots happening there. So in other words, if we have two matrices here, so this is our rows and columns, and this is our rows and columns. Then, in order for this to work, we've got to have this condition. So let's check that. Those two are matching up. And now, what's our resultant matrix going to be? Well, it's going to be the rows of the first matrix and the columns of the second. So we're going to get a 2 by 4. That's the result. Now, in order to find each position in our new matrix, we've got to find the dot product. And we'll show you how to do that in the example now. Okay, so in this example, we've got a 2 by 3 matrix times by a 3 by 2 matrix. And yes, this works because our rows of the first matches with our columns of the second, and our resultant matrix, this is going to form a 2 by 2. So we're going to get some sort of 2 by 2 matrix here. Now, what is going to go in each position? Well, if we just sort of quickly do a little bit of labeling, that's the first row, first column. This is the second row, first column. First row, second column, and second. They're the 4 things I've got to find. Okay, so just making that super clear. This little symbol stands for first row, second column. Okay, so let's find these 4 things, and I'll show you how to do that with the dot product. So, first of all, let's find the 1, 1. So to find the 1, 1, we multiply the first row by the first column. So we are timesing together these 2 columns. Columns are at least 1 column, 1 row. And how do we do that? Well, we take the first position in each one. So the first part will be 1 times 1. Then we add to that the second positions, 2 times 4. And then we add to get that the last position, which is 3 times 1. Okay, and so that will get us 12. Okay, let's try now the second row, first column. So that will be second row, first column. And we're going to get 2 times 1 plus 1 times 4 plus 4 times 1, which is going to give us 10. If I keep going, doing the same pattern, I'm going to get these 2 values, 1, 2, and 2, 2, which gives me so we get 21, and then 2, 2. we have 2 times 2 plus 1 times 5 plus 4 times 3 which is also 21. So our resulting matrix will look like this. So like our final answer for this one will be this matrix: 12, 10, 21, 21. Okay, so if you're doing B, have a go now. Here's the answer to B. If you follow that full process, you would get 1, 1, 2 by 2, Okay, so how did I decide it was going to be a 2 by 2? Well, we've got a 2 by 2 and a 2 by 2, which gives me a 2 by 2 matrix by following our sort of rule from before. So the rows are the first, the columns are the second. Okay, and so your answer then is 5, 6, 11, 23. Okay, question 7, row operations. So if we're wanting to solve a system of equations, we can use row operations, and there's 3 of them, to be able to manipulate a matrix. So it's basically reorganizing the matrix in order to solve it. So we're going to look at the first of those 3 rules, and the first one way that you can change a matrix is by swapping the rows of a matrix. And when we're actually doing these processes, the rows are referred to in shorthand, so row 2 would be R2. Okay, so if we look at this matrix here, 1, 0, 2, 3, 2, 1, 4, 1, 3. If we decided to swap row 1 with row 2, the matrix would now look like this. So we've swapped this row with that row. So in our new matrix, the original row 2 is now the first row. This is the row 1, and the row 3 had that as the same. Okay, so you're allowed to swap the rows. So A says swap row 1 with row 3. So the resulting matrix after doing this swap, so we're swapping row 1. Okay, we're swapping these 2 rows. And so our resulting matrix will look like this: 1, 2, 3, 0, 1, 2, 0, 0, 1. Try swapping a row for yourself. In this question B, they ask you to swap row 2 with row 3. So our resulting matrix looks like this. We rewrite row 1, and we swap the other 2 rows. In question 8, we can also, when we're doing row operations, we can multiply any row by a number. So you can like double a row, triple a row, I mean, if you go back to solving equations simultaneously, one thing you did to solve them was to multiply, like doubling a row, so you could do like elimination method, for example. Similar sort of concept happens here. So let's just consider this matrix here. Now if we multiplied row 2 by 3, so the operation is 3R2, the matrix would look like this. So we've taken row 2, which is this one here, and we've times it by 3. So we've done 3 times R2. So 3 has become 9, 2 has become 6, 1's become 3. Let's try an example. A, multiply row 1 by a half, i.e. do a half times row 1. Okay, here's row 1. So we're now going to, do a half R1. So our new row 1 is going to be a half of the old row 1. And so our resulting matrix is 1, 0, 2. And then we rewrite the rest. 0, 1, 2, 1, 2, 3. Okay, try multiplying row 3 by 2. Okay, so our new R3 is going to be equal to 2 lots of R3. So our resulting matrix will be, well, row 1 hasn't changed, row 2 hasn't changed, and row 3 becomes double it, so 2, 4, and 6 instead of 1, 2, and 3. On to 9. Okay, our last type of row operations is that you can add or subtract a multiple of another row. So if we look at this matrix here, if we replace row 2 with a sum of row 1 and row 2, the matrix would look like this. So in other words, we can replace a row, row 2, with the sum of 2 other rows. So we can actually we're adding row 1 to row 2, and then rewriting where row 2 was with that result. So to get this row 2 here, what we've done is we've added those two together. So 1 plus minus 1 is 0. We then added those, which gives us 1, then added these, and that gives us 3. So that's how we did it. So in part A, I'm going to replace row 1 by row 1 minus row 3. Okay, in other words, what I'm going to do is I'm going to change this first row. So the process I'm going to do is row 1 is going to become R1 minus R3. So when I do that, I take row 1 and so for example, I take 2 and I take away what that matching value is in row 3. So 2 minus 1 will give me 1. So 2 minus 1 will give me 1. 0 minus 2 will give me minus 2. And 4 minus 3 will give me 1. Okay, and then I just rewrite the rest of the matrix in. Okay, why don't you try B? So we're going to replace row 3 replace row 3 by row 1 plus row 3. So we're going to, row 3 is going to become row 1 plus row 3. Okay, so we're leaving these the top row, the middle row, and now the bottom one becomes 0, 2, and 4. For now, the determinant of a matrix. Now, you might wonder why you would do such a thing, but this determinant will have greater value in applications when you're solving systems of equations and in calculus, which we won't really get to in our short time in matrices. Now, the determinant can only be found on matrices that are squares. So it's got to be a 2 by 2 or a 3 by 3. And we're just going to look at the determinant for a 2 by 2 matrix. So if we think about this matrix here, A, B, C, and D are those 4 positions of the 2 by 2. The determinant is found by multiplying the diagonals and subtracting them. In other words, you do A times D and you subtract B times C. So let's find the determinant of this first one. So the determinant will be 1 times 3 minus 2 times 5, which gives us minus 7. Try B. The determinant in B will be 1 times 1, the diagonals, minus 2 times 4, which will also be minus 7. If you're needing to solve a system of equations, one way you can do that is by using your row operations to manipulate it to get into a particular form that tells you the solution. And this form is called reduced row echelon form. Okay, it's a mouthful, but what does it actually look like? Reduced row echelon form, if I was solving a system of 3 equations with 3 variables, would look like this. It's where the main part of your matrix has 1s on the diagonal and all other positions are 0. Those, what this is meaning is, because this is the x variables, the y variables, and the z variables, it means that the top line reads the equation, well, x is equal to 1 lot of x is equal to 2, 1 lot of y is equal to 3, and 1 lot of z is equal to 4. And so that's how we can read the solution off. So here's a system of equations. And if we converted that into matrix form, it would look something like that. Now, after doing a bunch of row operations, so swapping rows, multiplying, adding, it eventually reduces down to this. And from this, which is now in reduced row echelon form, you can read off the solutions. So in this question, your job is to be able to read off the solutions. So part A says, what is the solution to this system? Well, x equals minus 2, y equals 3, and z equals 4. Why don't you try B? The solution to B, x equals 5, y equals minus 2, and z equals 8. Okay, so the last question is a bit of a challenge question, and it requires us to be able to solve a system of equations using matrices. So we need to take our system, put it into this form, and then go through a whole lot of steps to get it into the form 1 with all the zeros into reduced row echelon form with some values for our answer. Like, that is the goal of this question. And some of these take more steps than others, and it can take a while to write them out. Let's have a go at writing out the first one. Okay, I'm just going to work down the page in 2 columns, and we will find out what our solution is. Okay, so here's the initial matrix. Okay, so let's get started. A strategy to completing these is to work at these values in the bottom first. So what I mean by that is we want to try and get these ones into 0 first. And once we've got all them to 0 and this into 1, you can then easily manipulate those top ones. So you want to start by trying to focus on these bottom ones. Okay, so the first move I'm going to make is I'm going to take row 2 and I'm going to subtract row 3 from it. And this will give me this matrix. And continuing on, so while I've achieved a little 0 there, you can notice. So my next step after that is I'm going to start working at row 3 to try and get a 0 there. And to do that, I'm going to take row 3 and I'm going to subtract 3 lots of row 1. And you can add or subtract multiples of other rows. And the reason I'm doing that is because I've got a 3 in the 3rd row at the bottom. And if I've got that 3 and I can use this 1 here by taking off 3 lots of that to get it down to 0. So when I execute this action, I get 1 minus 1, 1, 0, 5, 2, and now 0 minus 1 minus 6. So you can see I'm starting to make progress with solving that. Okay, so my next operation then is going to be swapping row 2 and row 3. And the reason I'm doing that is because I noticed a 1 in the bottom row. Well, it's a negative 1, but because it's a 1, it means I can easily change that to a 1. By subtracting the whole row by a minus, and then I've achieved my second row position that I want. So swapping it, I'm going to get so I'll just swap those 2 rows across. Okay, so I just missed a minus sign from before. Okay, so now I've swapped those. My next move after that is going to be minusing row 2. So row 2, all I'm going to do to it is I'm going to times it by a minus. So this means just times it by -1, putting a minus out the front. And so that now gets me this matricing. Okay, so I get 1. So pretty much I'm just swapping the direction of those values in there. And that's going to be helpful because it now means I've got the first 2 positions that I want. I want 1s across there and I want to try and get 0s along here. So my next target is to get that to a 0. And so the way I'm going to do that is I'm going to multiply R3. I'm going to take R3 and I'm going to subtract 5 lots of R2. And that's going to help me get that to a 0. So doing that operation, I get this 1 0 0 minus 1 1 0 1 6 minus 28. So I've got some larger numbers here, but they'll work out nicely before long. Okay, all right. So next step is now that I've got those zeros, I just want to make this bottom right hand corner a 1. And so to do that, the good news is that 28 goes into 84. So if I divide by -28, so to R3, I'm basically timesing it by -1 on 28. And that will then give me this. Okay, and so things are starting to look a whole lot nicer right now. So I'm getting closer. Now, next thing I can do now is manipulate, we might move on to a new page, is what I can do is now I can now use this final row, or the rows with zeros in it, to be able to turn others into zeros. So let's do the first step. So first I'm going to manipulate R1 by doing R1 plus R2. And what that does is that turns this first row second column value into a 0, because -1 plus 1 is 0. And then the way it changes the last 2 terms is I get a 7 there and 23 on the end. Okay, we're getting close now. Next step is now I want to make that value on the top, the 7, I want to make that into 0. And the way I can do that is by taking away 7 lots of R3. So R1 is going to become R1 minus 7 lots of R3. And this gives us 1 0 0 0 1 6 0 1 0 0 1, and my values on the end are 2 2 17 and 3. So my last step, my final step, is now to take R2 and do R2 minus 6 R3, and that will give us the form that we want and some values over here. So now we've finally made it there. We can now conclude that x equals 2, y equals -1, and z equals 3. So doing that process manually is challenging, but our goal is to be able to get it into that bottom form. So we've used what's called Gaussian elimination, so using the row manipulation, the row operations, in order to get it into reduced row echelon form to get our solution. Okay, that last one is really a challenge question. Good luck.